What if I told you Pete Crow-Armstrong didn't just have one style of play, but six? And what if I told you I could prove it using a method called principal components analysis? So, all right, today we're doing a PCA on PCA. That's right, principal components analysis on Pete Crow-Armstrong. I'm not a huge fan of grown people wearing player jerseys, but if I had to break the rule for someone not named Ken Griffey Jr., it's going to be for Pete Crow-Armstrong. This guy is just ridiculously fun to watch. Every game feels like a different episode. One night he's flashing gold glove range, the next he's legging out a triple, the next he's launching a ball 430 feet over the wall. There's electricity in the way he plays. And this PCA we just ran, it proves it. And I would flash you some video of all this. But MLB is so tight on the ownership of their content that I would rather leave it out than risk a lawsuit, notably given how long it took to put this together. So, we can run PCA on all the core categories: hits, home runs, RBI, walks, strikeouts, errors, and more. And hey, as someone living here in Chicago, I've got to say, watching PCA rise through the system, there's just this energy about him. It's raw, it's real, and you want to believe the next great Cubs era could start here. You can download the data in the tagged comment, and feel free to subscribe while you're doing it. First, why principal components analysis at all? We're looking at reducing 13 overlapping baseball statistics into several meaningful components in statistical fashion. We are grouping variables and have 13 continuous variables at our disposal. Okay, let's go ahead and run the principal components analysis model. First, I go to Analyze, then to Dimension Reduction, and select Factor. Then I move all my performance variables into the Variables box. These include at-bats, hits, runs, doubles, triples, home runs, RBI, walks, strikeouts, stolen bases, caught stealing, batting average, and errors. Under Extraction, I choose Principal Components as the method. This isn't factor analysis. PCA isn't trying to model latent traits. It's reducing complexity by summarizing variance across multiple variables. I keep the default criterion to retain components with eigenvalues greater than 1. Why? This rule of thumb ensures we only keep components that explain more variance than a single variable would on its own. I check the box for Scree Plot to visualize the drop-off and explain variance. Under Rotation, I select Varimax, which is an orthogonal method. Varimax helps simplify the output. It spreads the loading so that each variable loads clearly on one component, perfect for interpretation and storytelling. Then I hit OK and we're off to the races. So why do I use this method? First, PCA is an exploratory tool. I'm not testing a formal hypothesis. I'm exploring the data to uncover hidden patterns. I want to see how stats like home runs, strikeouts, and stolen bases cluster together without assuming what those patterns should be. Principal components analysis is an exploratory method, not a confirmatory one. It doesn't test hypotheses. It helps you uncover structure you didn't know was there. I choose principal components because I'm working with observed variables, not trying to infer latent traits like mental toughness. I use the eigenvalue greater than 1 rule to focus on the components that carry more variance than a single stat. This keeps the model lean and efficient. And I apply a Varimax rotation to simplify interpretation. I want each stat to tell me which component it belongs to. Ideally, one strong relationship, not 5 messy ones. I'm going to extend the thinking on eigenvalues in the analysis portion, but at this point, I want to stop and talk about the 2 rotation types. The 2 primary are orthogonal and oblique. Orthogonal is best when components are independent or uncorrelated, which is what we have here. You can't hit a double and a triple, and a stolen base is an independent event that cannot happen in addition to something else. Our goal here is clarity, not modeling nuanced correlations. This whole process is about exploration. I'm using PCA to reduce noise, surface structure, and find the real story behind the stats. By the end of this process, I've turned 13 stats into just a few interpretable dimensions, and now I can track which version of Pete Crow-Armstrong showed up to play in any given game. In this particular portion of this series on PCA, we're going to look at the communalities table. The rule of thumb in communalities goes like this. Values greater than 0.80 are considered excellent, noting that this variable is very well represented. Values between 0.60 and up to 0.79 are considered good and solid representation in the PCA model. For values of 0.40 and 0.59 are considered moderate, meaning the variable is somewhat underrepresented and may have unique variance. Finally, values below 0.40 are considered weak. We can say this variable is poorly explained by the components and may be a candidate for exclusion or further review. Now, should we have values in the communalities below that threshold, this suggests 3 possibilities. First, a poor fit to the component structure. we can suggest that the variable isn't well explained by the retained components. It may have unique variance or doesn't align with the dominant patterns captured by the PCA. Take, for example, a stat like batting average may be influenced by lots of small factors: defense, luck, contact quality. It may not cluster neatly with home runs, RBI, or walks. The second is the possibility of the variable being an outlier or noisy variable. The stat might be inherently inconsistent, like possibly errors, or caught stealing. It could also contain random noise, or have low correlation with other variables, making it hard for PCA to extract a meaningful pattern from it. Third, we might have potential redundancy or irrelevance. If the variable doesn't contribute to explaining broader patterns, it may be redundant, meaning already captured by other stats, or not meaningful in this context. For example, if hits and RBI load high but batting average doesn't, it could be because batting average is an indirect summary of other stats that are better captured directly. Now let's go through the actual variable extraction interpretations. First, at-bats, with a value of 0.742, means that 74.2% of the variance in at-bats is explained by the PCA model. Strong representation. And at 0.850, hits are very well captured. Hits are tightly connected to the component structure. Runs are also a solid representation at 0.702. Runs relate well to the extracted components. At 0.674, doubles are reasonably well captured. Triples have a value of 0.820, suggesting high communality. Triples are now strongly linked to key components, possibly speed or athleticism. Home runs have a value of 0.870. This is considered excellent. PCA is doing a great job capturing home run variability. This likely feeds a power component. RBI, a value of 0.774, which is a very strong fit, makes sense since RBI usually ride with HR and hits. Walks have a value of 0.710. Walks are clearly tied to a coherent pattern, perhaps a plate discipline component. At 0.608, strikeouts are moderately well captured, plenty of variability explained. And at 0.578, stolen bases are still a bit lower, likely due to their situational variability. On the other hand, at 0.681, caught stealing fits well, perhaps clustering with aggressive base running. Batting average is at 0.540, which is slightly improved but still modest. Batting average may still act a bit independently. At 0.612, errors are now more cleanly captured, likely part of a defensive. Having now reviewed the variable extractions, we'll move over to the more complex-looking table of the total variables explained. This output is divided into three sections. First is the initial eigenvalues, which is how much variance each unrotated component explains, before any filtering or rotation. Second is the extraction sums of squared loading, showing we only keep components with eigenvalue greater than 1, the ones you retained. Third is the rotation sums of squared loadings. After Varimax rotation, this redistributes the variance across components to maximize interpretability. Let me elaborate on a critical concept here in the eigenvalue. In PCA, an eigenvalue tells you how much total variance in the dataset is explained by each principal component. Here we've got 13 different stats that vary across 212 games. PCA compresses these into a smaller number of new supervariables, or principal components. The eigenvalue for each one says how much of the original data story is captured in this component. The rule of thumb we apply is to keep components with eigenvalues greater than 1. This is known as the Kaiser criterion, because a component with eigenvalue less than 1 explains less variance than an original variable, so it's not earning its keep. And in our case, our analysis kept 6 components because each of those had eigenvalues above 1. Together, they explain 70.5% of all the variance in your game-by-game stats. I'll also jump over to the Scree Plot. A Scree Plot visualizes the eigenvalues in descending order. You look for the elbow of the curve, where the drop-off in variance levels off. That elbow helps confirm how many components are truly meaningful. You can see we have it hit the inflection point of eigenvalue of 1 at 6 components. Now, to interpret our output, we see that we have 6 components retained. Together, they explain 70.5% of the total variance in our data. It's excellent. In social science or performance data, anything above 60% is typically solid. 70% plus is especially strong for individual game-level sports data. Now, what this tells us about the PCA model is that we have extracted interpretable and meaningful dimensions. Each component captures a unique piece of the story. The Varimax rotation smoothed out variance, so no single component dominates, making for a more balanced and communicable analysis. Now, to the most critical stage of our analysis, we turn to the component tables. The component matrix shows the correlation between each original variable and each principal component. Think of loadings like membership strength. A high loading like those above 0.60 means that variable contributes strongly to that component. This is the unrotated solution, so it's not quite as clean as the rotated version, but it's still useful to understand the raw structure PCA uncovered. The unrotated matrix shows us how variables align naturally with components, but it's often like reading tea leaves. Rotation, especially Varimax, spins the statistical lens just enough to clarify the picture. Cleaner clusters, stronger patterns, and easier component naming. Imagine you scatter plot your data, and PCA draws two axes at weird angles that best explain the spread. But they don't line up cleanly with any one group of variables. Rotation is like spinning the axes until each one points directly through the clouds of related variables. It doesn't change where the data points are, just how we name and interpret the directions. So what does this matrix tell you? Each number in the table is loading, a correlation between a stat, which is the row, and a component, which is the column. Higher absolute values, typically those above 0.5, indicate a strong relationship. Our components are now interpretable dimensions of Pete Crow-Armstrong's performance. What we can take away from this table is the patterns about the data, the observed variances, tell us the thematic story, and in this case, we have reduced 13 variables into 6 components, or super variables. Let me quickly run through a rule of thumb on interpreting component loadings. Values above 0.70 are considered very strong loadings. I want to make a few additional notes. First, we typically want 2 or more variables loading at 0.50 or higher on a component to consider it well defined. But in exploratory PCA, loadings of 0.40 are often considered meaningful, especially in social science or sports performance contexts. We also want to watch for cross-loading variables. If one variable loads at 0.4 or greater on multiple components, it may muddy interpretation unless it's theoretically justified. Now, to the actual point of this whole thing, let's talk through the loadings. Component 1 has 3 key variables very strong, with home runs at 0.909, RBI at 0.845, and runs at 0.700. This component clearly captures offensive impact and power output when PCA drove in runs or hit the long ball. We will also note that hits load strongly on Component 1 and Component 2, which meets the consideration we just discussed on cross-loading variables. That said, with the warning being that we need to be able to theoretically justify, we can see that hits may have strong contribution to both components and speak to the theme about the loading. Hits are a critical summary of both power as well as what Components 2 looks to be representing contact and gap power. This component reflects games where PCA wasn't necessarily hitting home runs, but was consistently barreling balls into play, finding gaps, and racking up hits. The key representative variable is doubles at 0.803, but supported by hits, which are general hit production, and batting average, which is contact efficiency. To Component 3, we have stolen bases and walks as combined high-load variables. This would suggest the concept of a table setter. This component reflects games where Pete got on base without needing to hit, and then used his speed to pressure the defense. Classic leadoff energy. Get on, get moving, create chaos. It's reminiscent of opportunistic leadoff behavior. Component 4 looks like an aggressive plate approach. Strikeouts and at-bats loading high with a moderate negative of batting average suggests the trade-off that comes from contact efficiency. This reflects high-volume games with more swing and miss. He got his chances, but likely chased or struggled to convert. Component 5, we have what looks to be base path and fielding risk. This is high load for caught stealing and errors. Theme is defensive and base path choas. These are games where things got messy, defensive miscues and aggressive base running backfiring. Finally, Component 6, solely loaded in strong fashion to triples, which, if you've watched enough baseball, you know it's often the most difficult trackable stat in the game. The theme here is rare hustle play. This is likely a specialized component. Triples are rare and behave uniquely. SPSS spun off a component to account for this pattern on its own. In summary, we have the following. Component 1, when Pete was the centerpiece of the offense, Rod. Component 2, when Pete was spraying doubles and piling up hits, think gap-to-gap guy, not 3 true outcomes. Component 3, when Pete was the spark plug, drawing walks, stealing bags, and setting the table. Component 4, when Pete swung a lot and missed a lot. Component 5, when Pete's hustle hurt more than helped. Component 6, when Pete flew around the bases. The final portion of this analysis is that of the component transformation matrix. The matrix shows the mathematical transformation applied to rotate the original, unrotated components into their new rotated positions. You can think of it as a rotation blueprint, which is how the analysis reoriented our axes to produce cleaner, more interpretable component loadings. It works like this. Each row represents an original, unrotated component. Each column represents a rotated component. The values are cosine-like weights that tell you how much of each original component is contributing to each new rotated one. The translation is it tells you how SPSS spun the axes from the initial component space into the final rotated structure using orthogonal rotation, where Varimax equals uncorrelated components. You don't typically interpret this table directly like you would the rotated component matrix. This matrix shows how SPSS mathematically rotated the component axes behind the scenes. We don't interpret this directly, but it's essential for understanding that rotation doesn't change the data, it just makes the components easier to read. Think of it like adjusting the angle of a camera. The scene is the same, but your perspective and clarity dramatically improves. Living in Chicago, I'd love nothing more than to see this guy become the real deal. He's electric on the base paths, fearless in center. You can tell he wants it. So yeah, maybe this is a nerdy way to root for a player, but I genuinely hope we're watching the beginning of something special. Drop a comment down. Who should we PCA next? If you want to see how this is built step by step, check the description of the full data and code walkthrough. If you like this breakdown, hit that like button and subscribe for more data-driven sports analysis.